Yeah, I changed the title, but the topic is similar. I just emphasized the dark matter part. Good. I don't know if you have seen, how many of you look at the New York Times in the morning, but this morning the New York Times title was this one. The person who wrote this title clearly doesn't believe that Lewandowski didn't do anything illegal. Do we? I'm not sure. But we are friends of Jurek nevertheless, enormously. And I, for me, Jurek has been a friend, has been a continuous source of inspiration for physics. And in fact, I was a bit shocked. What was it? A week ago, 2 weeks ago, because I got the advertisement about a prize for a Polish scientist and a French scientist who would work together, who have worked together and done things together. And I thought, oh, that's me and Jurek. I mean, that's because I work in France and he works in Poland. So I said, well, let's self-nominate ourselves for the prize. And I looked at the list of papers we had together, and in fact, it's nearly zero. And I was completely shocked because I've been inspired by what Jurek has been done through the year in so many things I've done, and I think quite a lot vice versa. I mean, you've been there are pieces of physics in the sort of loop world which have been done by Jurek and I back and forth, but we have almost not collaborated except for this wonderful piece of paper here. Ted, where's Ted? Oh, Ted, do you remember this paper together?
I mentioned this paper.
Yeah, I know you mentioned. I know you mentioned it
when I introduced Ted.
Yes, in fact, it's the only thing we have done together.
Yeah, so it's true. We are almost like Maria Skłodowska and Pierre Curie. However, we have to legalize it, make it official.
Yeah, I'm Pierre. Right, and you're Maria. That's right. Anyway, we have no chance for this prize because I don't think on the basis of this alone. But Jurek for me has been not just a source of inspiration for physics for all these years, but also a great friend. So, in fact, a wonderful friend. It's in this community has been a person I've always trusted and loved and considered a close friend. So I dedicate this to Jurek, my friend. This is back to the title. I'm going to talk about black holes evolving to white holes, the quantum tunneling from black holes to white holes, and what loop quantum gravity says about that. A number of you were in Penn State for the Loop conference a month ago, or whatever. There is some overlap. There's quite some overlap between what I'm going to say here and there, but there are other things which I'm going to say here which I did not say there, and in particular I will talk about the stability of white holes due to quantum gravity. I think it's a nice little aspect of the quantum physics of white holes, which is new as far as I know. But before going into that, I will, for those who were not in Penn State, I will sort of rapidly go through the main ideas of the black to white hole transition. So the overall, I can't see there, the overall story is roughly this one. I'm talking about dark matter. Dark matter, I think, is something we should focus, because dark matter is the only really mysterious aspect observed, the really mysterious phenomena observed in fundamental physics, which we do not understand. There are all sorts of theories about dark matter, of course. There are maybe 10 different theories, but none really convincing and all a little bit patchy. Everything else could be, everything else within the sky and in the laboratory could be, after all, explained with standard model appropriately extended general relativity, dark matter is strange. So it might be that in dark matter there is something related to quantum gravity, and I want to say that this is actually a real possibility, and this is what I'm exploring here. Now, it is an old idea that dark matter could be a Planck-sized particle, microgram particles, microgram little things flying around in the galaxy. A microgram is very small in astrophysical terms, is huge in particle physics terms. But it's a scale which is obviously there in nature, and it might appear, it might be there. Empirically, there are experimental windows that let the possibility offer the dark matter is just Planck-sized things that interact only gravitationally. So they have the Newtonian force, the gravitational force, and this is it's an idea of this Planck-sized things that were called Planckions. As far as I know, it was first suggested by these people here. This is a paper I just very recently discovered. In fact, it's Pierre, my student, who pointed out to me in '87. Much more known is this paper by McGibbon, same year on Nature, but just a little bit later, which sort of has the same idea. Then there's a long tradition of working on that. So it's one of the hypotheses that there are these Planck-sized things, and it's an old idea that these could be produced at the end of black hole evaporations. So if there are primordial black holes, which there's a quite open possibility that in the early universe were formed, they evaporate. At the end of the evaporation, they don't disappear. They might remain in the form of remnants, which are Planck-sized particles. This is an idea that has been bounced over and over again for a very long time. What's new? There are two things new. One is that these remnants, these Planck-sized particles that are left over at the end of the evaporation, have today, and I'm extremely surprised that was not noticed before, because you don't need quantum gravity for that. There is a physics that make them possible, which is classical general relativity, and there is a classical solution of general relativity, which is white holes, which could describe them very, very well. In fact, there is an old idea that these Planckions were cornucopions. This is expression used in the 90s. Space-time has a small throat and a huge space inside, and this is exactly what a white hole is in some foliation, if you choose some appropriate foliation. Now, one reason I believe this was not considered seriously before is that a white hole are classically unstable, so it's an exact solution of the Einstein equation, but if you perturb a little bit, there's an unstable. They're unstable in the sense that it changed into something else being a black hole. Okay, so if you take a white hole and you just send some extra energy near its horizon, what happened is just it tunnels into a black hole. A white hole can easily become a white hole, right? Just think Kruskal. The novelty, which I'm going to discuss today, is that quantum gravity may stabilize these Planck-sized white holes, making them stable or nearly stable. And therefore support the idea of Planck-sized particles floating around the universe, generated by the end of the evaporation of primordial black holes, which form dark matter. So, a few words about white holes, because white holes are still white holes are very simple things, right? A pure classical GR, but they're still hard to digest for very often. The first observation about white holes is that the external of the white hole and the external of the black hole are not distinguishable at all. They're exactly the same metric, right? If you're outside the horizon, say you're a 2m plus epsilon, whatever you measure, you don't know if you're outside a black hole and a white hole. In fact, in both cases, you're just in region 2 of Kruskal. So if you start from Kruskal, a physical, astrophysical black hole, there is some matter that enters into the horizon here, collapses. You forget all this part of Kruskal. There's no the other asymptotic, and you have the external and the black hole and the horizon. A white hole solution is the opposite, is a time reversal of that. So imagine you have some matter that comes out of the white hole, and you have the external. So if you're outside, the only difference is that if you look back, at some point you have matter here. If you look in the future, you have matter here. But this is the horizon of the white hole. This is the horizon of the black hole. If you draw this in standard sort of Schwarzschild-like or radiant Finkelstein-like coordinate with the r, you have an horizon. Whether this is it's an horizon with the light cone is like that or like that, you don't know. I mean, the outside is exactly the same. Classically, a black hole solution of the Einstein equation becomes unreliable here near the singularity, which is quantum gravity, and a white hole becomes unreliable here. The novelty is that there is increasing evidence from a number of different calculations from many people that the future of what happened here could be what happened here. So what happened at the end of the life of a black hole is mysterious. What could happen at the beginning of the life of a white hole could be mysterious. They could be the same thing. So a black hole can go into a white hole. So this is a scenario which is increasingly studied by many people from various possibilities. You have some matter collapsing, a black hole forms. This is the trapped region. You have a quantum transition. Then you have a white hole. This is a scenario. This is the main parameters as a lifetime of the black hole. Okay, say the advanced time here, the lifetime of the white hole, which don't need to be the same, and the mass. Notice that, let me take away this, notice that the horizon is a dynamical horizon that Yonggi Ma was talking this morning, or a trapped horizon, if you want, the boundary of the trapped region is not an event horizon, because quantum gravity acts here and stop the horizon. The information loss, which would be a long discussion, which I'm not going to do unless you want to raise it in the question in the session, is solved here naively because information that comes here goes out. And in our community, there's a lot of people who have worked on pieces of these stories from various perspectives. Whoops, what did I do? There's something wrong. I pushed the wrong button. All right, so this is the full space-time. The first element that supports this possibility is something which was not noticed before and was found out in just 3 years ago, which if you just allow quantum gravity to act in this region here, which is compact, so it's a finite just outside the horizon and for a short time, all the rest, so the outside, the black hole and the white hole, together form an exact solution of Einstein equations. Okay, which is not a portion of Kruskal, is in fact a portion of two Kruskals attached. You take one Kruskal solution, you take another one, and you cut it here, and you realize that obviously you can glue this line here and this line here, you glue them together, and then you have a single solution, which is an everywhere solution of Einstein equation. You have a black hole here, sorry, a white hole here, a black hole here, and you have a violation of Einstein equation along this line where there's singularity, and in a little region here, which is where the quantum gravity gives a tunneling possibility. The time scales are, in my opinion, still debated. There is a lot of heavy technical work. Simone is here. First of all, as I said, the lifetime of the black hole and the white hole might be different. This was pointed out, it should be different, most likely. This was pointed out by De Lorenz and Peretz just immediately after finding the time symmetric solution. There was a lot of attempt to use this spin network covariant loop quantum gravity formalism to compute this lifetime here. I don't think it's cleared yet. It has to be shorter than m cubed because there's a Hawking radiation that shrinks this. So the horizon here shrinks because of Hawking radiation, and in a time m cube in natural units, you start from a macroscopic black hole, becomes Planckian. And I'll show you in a moment that then it has to do this transition. So that's the maximum time, and the minimum time is m squared because before you don't, I'm not going to the argument, you don't expect quantum phenomena at all. So between these two times, and let's say at least m cube, something quantum gravity should happen in this region B here. And what is going to happen? Let me talk about the other region, the region A. So if you forget what happens here, and if you just imagine you're here and you're going toward the singularity, what is going to happen? This has been studied with loop quantum gravity using loop quantum cosmology techniques recently by various groups in the US and in Germany, and the result is very beautiful. You go from the black hole solution of Kruskal to the white hole solution of Kruskal, going through this the singularity. So you tunnel through the singularity. Of course, if you only look at this, this is an approximation, which is the utility of this is you have to cut this on the left because where there is a star, and you have to cut it on the right because there is the B region, which I'll mention in a moment. The effective metric through you can write an effective metric. This is a simplified version of the effective metric. I'll come back to that in a moment. This is the L is sort of Planck related. Quantum-related constant. This is a metric which is just Kruskal, internal of black hole here and internal white hole here, and it smoothly joins the two. Now, what about the B region here? We are again trying to compute a quantum transition here. Now, if the horizon has shrunk all the way down to the end of the Hawking evaporation, this is a Planck size horizon. So the B region is Planckian altogether. Okay, and the calculation we are trying to do is to use covariant loop quantum gravity to go from the past to the future of this region here. We use some coherent state on the past, some coherent state in the future. I see coherent state on the T-shirt of John in the first lines. We use this state, and then loop quantum gravity gives the probability amplitude. The probability amplitude we have got is exponential in minus the mass in Planck units, which means that is suppressed as long as the hole is large, but it's not suppressed when the hole is Planckian. So once you get there, the transition probability, it becomes of order 1. You just jump to the other one. So the horizon becomes like that. If you want a black hole horizon becomes a white hole horizon. In doing this, the topology of this thing here is S2, because this is a two-dimensional representation of four-dimensional space-time, cross a little diamond here. And if you want to triangulate this, is very hard. So we're not using the loop quantum gravity covariant transition amplitude with a triangulation, but we're using the one without a triangulation, namely the Warsaw version of it, not the older sort of Marseille version of it, which was written down by Jurek and Kamiński, Kieslowski a few years ago. This is one of the many, this is an amplitude that we wrote in one way in Marseille, and then Jurek translated another way. Now we're using Jurek way. It's one of the many examples of this back and forth between France and Poland on this in loop quantum gravity. This is a spin network of the boundary. I'm not going into detail. This is spin forming the inside. Now, what's the geometry? This is a simplified version of the metric inside. You see, there is this is the theta and phi coordinate, and x is along this direction here. As long as you stay away from the two boundaries, there is a translation symmetry in x, of course, like inside a black hole or a white hole. And you see what's going on. As tau grows, goes from a negative value here to a positive value here. This is tau equals 0. So when tau grows from negative to 0, the radius of this shrinks and the length of this becomes longer. They don't go to 0, this doesn't go to infinity, get to a minimum L and to a maximum L, and then bounces back. So what you have inside, in this foliation, the black hole is this long tube that becomes long, and narrow, get to a minimum, and then comes back. And it's important to notice that at each point along the horizon here, the internal is different depending on how old is a black hole. Right? So the no-hair theorem is something that has to do with external, not with internal. An old black hole of mass m is completely different than a young black hole of mass m internally. All right. We have actually worked out the metric inside, taking account also of the back reaction of the Hawking radiation. There is some flux of energy, positive flux of energy, which is a standard Hawking one. There is some negative flux of energy that goes in. We're very confused about this negative energy. We realize that this is the case in which the matter forming the black hole is a null shell. When the negative energy crosses the bouncing out matter, it becomes positive energy. So what comes out is always positive energy. Positive energy, Hawking radiation, positive energy, what remains of the mass coming in, and positive energy, what is the negative energy of the Hawking radiation, sort of absorbing energy from this when crossing the bouncing matter. So the Bondi mass that you see here on Scry Plus, first is this black hole mass, then it goes down because of the Hawking radiation, then it goes down again, it goes to 0, it never goes up. This color, in this approximation here, the metric inside is always locally a sort of Vaidya metric. So it's a Schwarzschild with varying mass, and the color code the mass. So the mass is high here and goes down here. And since I'm often accused, blamed of never putting equations in my talks, just putting pictures, because I think in pictures, this is actually the metric explicitly, just in case you wanted to look at it and check it. All right, so going to remnants, we're after the transition here. This is the white hole. In this foliation, which is essentially the constant, more or less the constant Schwarzschild radius foliation, almost is a minimal maximum volume foliation, but is, except on the horizon itself, is very close to the Schwarzschild foliation. So in this foliation, on each Cauchy surface here, the geometry of the inside is this long tube, which, since we are past the transition, this is now growing and coming back, and it takes time, right? It takes a long time to come back. Now, this is let me come back. This is a white hole. So classically it's unstable. That's where I want to go. The physics of that is, since it's very long, it holds, it can hold long wavelength modes, as many as it wish, because it's very, very long, right? And therefore it has a lot of possible internal state distinguishable from one another, a white hole. So the white hole is small. The throat is small, but it's very long, and it can have different states inside. But they're very long wavelength, so very slow frequency. So whatever comes out very slowly. That's what makes it interacting a little with the inside. So it's exactly what the Planckian hypothesis was at the very beginning. A small particle with a lot of internal states, which interacts very weakly and only emits very low frequency particle. Now I want to try to understand that there are a lot in the literature of argument from quantum field theories that something like that should be nearly stable. What stabilizes it from the perspective of quantum gravity? Let me consider a Cauchy surface that cuts through the horizon, and let me consider the state of matter and geometry inside, from the horizon inside, for a white hole or for a black hole. And let me call it, let me simplify, or forget all the degrees of freedom, except whether it's a black or white hole, the mass and the volume, how long it is. So these are the states I want to consider. So this is a coherent state of gravity that has that represent the geometry and eventually the matter here. Now, these states evolve, and how do they evolve? There are four processes, four things that happen to these states. First of all, as I said, the volume in this foliation, the volume of the black hole keep increasing, and the volume of a white hole keep decreasing. Okay, so in a DT, the volume increases for a black hole, decreases for a white hole. This is classical GR. You work out how much. This is dV over dt. This is Einstein equation, nothing else. Then there is a white to black instability. And the white to black instability has been studied by a number of people. The sort of consensus, even if I'm not totally convinced, but the sort of consensus in the literature is that the lifetime for a white hole going to a black hole is of order m. Then there's a Hawking evaporation for black holes. So a black hole of a certain mass loses mass because outside there is a standard process of Hawking evaporation. So you look at the standard theory of Hawking evaporation, and the mass decreases with this rate here, which is standard Hawking theory. And then this is the quantum gravity input. This is classical. This is quantum field theory on curved space-time. This is classical GR. This is classical GR. This is playing with Einstein equations. This is quantum gravity. And as I said, the present result of our calculation is that the probability is suppressed by the mass of the exponential minus the mass of the black hole. This is a probability per unit of time. So you put all together this, and you say, okay, let's consider a state with two components, B and W, which evolve with a Schrödinger equation. The time here is a asymptotic time, and I can represent this all these processes. If you want to model all these processes with a single Hamiltonian, which has all of them, has the transition from black to white, the transition from white to black, the change in the mass, the change in the volume, and so on. And now there is a key input. The mass only goes down, right? So because of Hawking radiation. So this want to decrease, but it cannot decrease continuously to arbitrary small masses because of the area gap, because there is a minimal area of the black hole, and there is no continuity between a small area with a long thing inside and Minkowski space-time, right? So when you keep going down the mass, at some point you sit on the minimal mass eigenstate. And the dynamics here seems a bit complicated, but in reality the time scale are very different, and it's easy to see what happened in the various phases. This term here dominates until the black hole is macroscopic. This is completely suppressed. This is not there if you start from a black hole. This is not there if you start from a black quark. So the only thing that happens is that the volume increases and the mass goes down. The mass goes down, and you get to the minimal mass, and at that point you can represent on the minimal mass eigenstate this Hamiltonian evolution with just a simplified Hamiltonian on this sort of two-state system, and the system wants to sit on its minimum eigenvalue of the Hamiltonian. So you analyze this. The minimum eigenvalue of the Hamiltonian is just a linear combination of a black hole and a white hole of the same mass. with a ratio between the two that depend on these A-B parameters, which are of order 1 and are not sufficiently fixed. The models too vague to fix them. So the story here is that, if you want, let me put it in words. The black hole evaporates, make a transition to a white hole. The white hole is unstable and could go in something else, but in what? There's only one thing it could go into a black hole. So you have something that a black hole could transform into a white hole could transform into a black hole. And in quantum mechanics, you know what happened, you just go to a linear combination of the two. And you have the stable particle with a mass, which is a Planck mass, microgram, which just sit there. Okay? So this is a final picture. You have a primordial black hole, it evaporates, and then there's a transition to black to white quantum transition. There is a white hole instability, but go back and forth in a sense, and sits down on the minimal energy eigenstate. So there you have this remnant, this quasi-stable black hole. Now, this is quasi-stable, but remember that the volume is coming back. So there's the volume of the white hole is decreasing. At some point, when the volume is sufficiently small, it might make a transition to Minkowski space. The thing can disappear. White hole disappears, right? If you wait long enough for a white hole, it emits all whatever mass is energy inside, and it disappears. Classical evolution. And there are a number of arguments, which I don't have time to go through, to say that the lifetime of the black hole has to be of order m04, where m0 is the original mass of the thing, of the primordial black hole that collapsed. Now, let's suppose these are dark matter particles. This is a component of dark matter. Then it should be still here after Hubble time. So M4 should be larger than a Hubble time. But it should have already evaporated. So since formation, which is very early universe, M cubed time should be before. So you get a bound on the original mass, which is between M cube and M4 in Planck units, which give you this range of masses here for the original black holes that had enough time, to evaporate and become white hole, but not enough time to die as a black hole. Now, according to standard primordial black hole formation theory, the black hole form when their Schwarzschild horizon is of the order of the Hubble horizon, which means that this is the cosmological epoch when you translate that into the Schwarzschild radius of this size here. So the universe is very small. And this is exactly just after inflation in standard cosmology when you expect black holes to form. So there's a certain consistency here. If black hole formed at that time, they might be there. So that's one possibility. There's another possibility, which I don't want to go into much, but it's very interesting, that all this could have happened before the bounce. If there was a bounce, and in our community we have good arguments to believe that there was a bounce, then any primordial black hole, any pre-primordial black hole, any black hole from before the bounce, which have become a remnant, should be there. The remnant could go through the bounce, okay, and remain a very stable, quantum gravity supported Planck size particle. So that's my conclusion. First of all, what happened at the end of the evaporation of black hole? They tunnel into white holes. It seems to me that there is no other alternative which I find credible. What happens, which is uncontroversial because I find it, what happened at R equals 0 in a black hole? You just go through the trapped region to the anti-trapped region, which by the way is an old idea that goes back to the 50s to Singe. space-time continues in a white hole, which is not elsewhere, it's just in the future of the black hole. And this transition and the remnant can play a role and be a component of dark matter. There are also other possible astrophysical consequences of these white holes, but I haven't talked about that. Cosmic rays and sources of fast radio bursts. I'll focus here on the dark matter one, which I find it particularly intriguing. Thank you.
I guess there will be many questions and comments. Professor Piornicki.
Do you have any idea what are these micro black holes made of? Protons?
Yes. If they are,
Imps?
yes, if they are made in the early universe, then it's photons. Inside is photons, because that's what was around mostly at the time. So it's high-frequency photons that in the high temperature of the early universe, there are fluctuations, and these fluctuations might go into black holes, and what is trapped is just the matter that was around at the time that was photon. If they're pre-bounce, anything, because any collapsed thing pre-bounce may have given
some people claim that the important property of dark matter is that there is a special scale of acceleration that's present. I mean, that essentially tells you when about the transition from Newtonian to dark matter region. Do you have any indication in this model that this scale of acceleration may be
No, I don't
present?
see this here. I know what you're talking about, and I know it's intriguing. And is this A0? What is whatever? Right. I don't see it here.
What happens in de Sitter space? Does this transition to white hole remove the singularity at the future horizon? When you write the Penrose diagram, you know the future has singularities. If you have a white, if you have
Oh, you
a
mean the
black
de
hole.
Sitter
In de Sitter
singularity?
space, yes, and the future. Does it remove anything? Is it just because normally when we have black holes, in black hole de Sitter solution on a Penrose diagram, we have on the future we have the singularity still.
Oh, the black hole de Sitter.
Yes.
Okay, I was confused because de Sitter itself has no.
No, black hole de Sitter. Yes. Does it remove the singularity?
Yes, because let me think. I'm not saying something stupid. Yes, no, because it's because this is completely local. So there is a big separation of scales. To the extent that the mass of black hole is small compared to the radius of the universe, then what I said for asymptotic space-time is also true for a black hole sitting in a de Sitter universe.
Yeah, but singularity is always small on the future horizon of de Sitter, but whether it disappears completely, that's my question.
Instinctively, I would say, instinctively as a physicist, I would say yes. If you ask a mathematical physics problem, I don't know.
Okay.
So I was wondering about the...
Hi, Thomas.
Hi. So I was wondering about abundances. So if you look at the dark matter content in the universe, you could probably calculate the density of dark matter, and then there's the possibility that these things can clump, right?
Yeah.
Do you know what the probabilities for this to happen is? And
there's a good news and a bad news. So for the model. The good news is that you can assume. Let's assume that all of dark matter is that, for simplicity, and let's compute how many of these are around. And then what you find is that there's one of these Planckion, this Planck's microgram particle. This has the weight of a hair, right? Floating around per volume of a solar system. So in the solar system, there's one of two of them. Now you may say, well, what am I? Because most of the intergalactic space is empty. So the dark matter density in the galaxy is roughly the same of the matter density, is a bit higher, but normal matter is concentrated in stars and systems, star systems. Dark matter is presumably more. So locally, there's just a few of these things floating around. The way they interact is only gravitational, is dust, so it fits exactly the cold dark matter model. So everything that has been computed for cold dark matter model works very, very well. So this is it, could be it. Let me tell you the bad news. The bad news is that suppose all of this is dark matter, then each single one of these come from a black hole, which was much heavier. So you need the primordial black hole, the sum of all the mass of the primordial black hole to be a lot to evaporate and then remain each one Planckian. So you have all this extra energy, if you want, that we are far from sure, and there are doubts, it's accounted for the standard cosmological evolution.
Thank you.
Okay. The last question.
So let me ask a naive question. At certain point, you mentioned that there are Cauchy surfaces which play some role. I couldn't get the point. How important is the use of those in the argument? I mean, if you show me the figures, I think these are not Cauchy surfaces for the space-time regions.
This one?
Yeah. I mean, the past, for instance, for the black hole version is completely covered by the Cauchy development, but the future is not. So the singularity is not completely covered by the Cauchy development of that Cauchy surface. Vice versa. You know, the singularity of the white hole is not covered by the Cauchy development of that surface. This is a partial Cauchy surface, but the whole space-time region you show is not globally hyperbolic with respect to that space-like slice. I'm curious, if it is important for you or not. I mean, in evolving the quantum states.
Yeah. Yes and no. Let me say why yes and why no. You're right, because this is a space-time we're considering, right? This is the actual space-time we're considering. So if I draw a Cauchy surface here, this is R equals 0. So this is a Cauchy surface. Then if I evolve in the future, it hits this quantum gravity region. So you're right. Then how do? But in that sense, you're completely right. It's not a Cauchy surface. But we're doing quantum gravity. So we have a calculation of what happens here, and we have an effective metric that covers all this tunneling region, which is not a solution of Einstein equations, of course, because there's no solution of Einstein equations. It violates Einstein equations, but we have written it explicitly. So with respect to this metric, this is a Cauchy surface. If you think of quantum gravity just a correction of Einstein equations somewhere, with respect to this corrected dynamics, this is a Cauchy surface.
After we will thank Carlo for the talk, there will be 20-minute coffee break.